Okay, welcome to section 7.6. This is a section about something called common logarithms. So we're going to use a lot of the tools that we already know about logarithms, and we're going to focus on a specific kind of logarithm called the common logarithm and how we use it. So we're going to talk about solving exponential equations and inequalities using common logarithms. This is where we're going to learn, like I told you about in section 2, when you cannot write each side with an equal base, what do? That's what we're going to talk about today. And then we're going to learn about something called the change of base formula. That is another way to evaluate logarithms. So please be on the lookout in this section for these two vocabulary words, common logarithm and change of base formula. So the first thing we're going to focus on is common logarithms. Common logarithms are logarithms that are base 10. We call these common logarithms because they are very common. They come up in applications that have to do with earthquakes, with sound, with measuring different kinds of things like that. They just come up a lot and in different scientific applications as well. So a base 10 logarithm, which up until now we've seen it written like this, log base 10 of x. But we can write them without the 10, without the subscript. So if you see this, log of x, you should automatically think that there's a 10 there. It's exactly the same as when you see a square root. You know that technically there's a 2 there. It's a square root. But it's the most common one, so we don't write the 2. We just know that it's there. Same thing with log of x. We know that it has to be base 10 if there's no subscript written there. And most scientific calculators have a key that allow you to evaluate common logarithms like that. So if we look here at this scientific calculator, this is our log key, and it is log base 10. So if we wanted to evaluate, let's say, the log of the logarithm base 10, let's see if it'll let me click that, logarithm of any number, let's say the logarithm base 10 of 2, we can just put that in and click, and it will give us the decimal representation. So if we come back over here to our PowerPoint, our first example involves using your scientific calculator to evaluate. So you should get out your calculator, the one you're going to be using in class. You're required to have a scientific calculator. You should get it out and make sure you can find where your logarithm button is and try to evaluate this, log of 6. So when you put that in, when you click log 6 and enter, you get 0.7782. Notice it's a 1 here and a 2 here. That's because they asked you to round to the nearest 10,000. That's 4 decimal places after the decimal point. All right, so let's check how you guys are doing. Try this using your calculator. Okay, the answer here should have been B. All right, sorry this is kind of a bad quality picture, but I just wanted to point this out. Common logarithms and logarithms of things that are different by a power of 10 are very common. Remember that logarithms are exponents. So for example, if I have the equation y equals the log of x, that's log base 10 since I don't have a subscript written there. That's log base 10 of x. That means that y is the power, right? If we wanted to write that in exponential form, we would write 10 to the y equals x, which is actually what they show you here in the first line. So y means what power do I need to raise 10 to get x? So for example, the log of 1. Again, no subscript, so we know it's 10. It means 10 to what power equals 1? That has to be 0. It means 10 to the 0 equals 1. Log of 10 is 1. Why? Because that's log base 10 of 10. 10 to what power equals 10? The power of 1. Right? So log of 10 to the m equals m. Why? Because if I have log base 10 of 10 to the m, well, m is the power that I would need to get there. So for example, if I see log of 10 to the 7th, if I see log of 10 to the 7th, then I can say, okay, well, I know this is technically a base 10 here, even though it's not written. 10 to what power gives me 10 to the 7th? Well, 7. You can almost think of the base here and the base of the exponent as undoing each other. They're kind of inverses in a way. All right, so let's take a look at this example that has to do with jet engines. It says that I have an equation here that gives me the loudness of a sound, 10 times the logarithm of L over M. That's an L, not a 1. Where L, or I guess it's probably supposed to be I. I is the intensity of the sound. M is the minimum intensity of a sound detectable by the human ear. It says the sound of a jet engine can reach a loudness of 125 decibels. How many times the minimum intensity of audible sound is this if M is defined to be 1? So they're telling us what M is. They're giving me the loudness, and they want me to find the intensity and figure out how many times the minimum intensity, the loudness, is. So here's my original equation. And notice I know the loudness is 125, so I replace L with 125. And I know that M is 1, so I replace that. I divided by 1 is just I. Then what they did to get from this step to the next step is that they divided both sides of the equation by 10, because this is 10 times the logarithm of I. So I divide by 10, 125 divided by 10 is 12.5. So I have 12.5 equals the logarithm of I. Again, subscript here means that there's a 10 even though we don't write it. So I use my definition of a logarithm to write this in exponential form. 10 to the 12.5 equals I. And then I can just use a calculator to figure out that that is 3.162 times 10 to the 12th. That's scientific notation because the decimal is so big. And so the sound of a jet engine is approximately 3 times 10 to the 12th, which is about 3 trillion, times the minimum intensity that a human ear can detect. Okay, moving on to some other ways to solve exponential equations. Remember in section 2, we talked about like if I have 3 to the x equals 9, well, if I can rewrite both sides of my equations with a base of 3, then I can solve for x easily. But the problem is sometimes that does not work. If that does not work, and I have a variable in the exponent, then I solve by taking the logarithm of each side. So this is going to be a new strategy that we're going to be practicing in this section that you need to take note of. So if I can't do this, rewriting with the same base, I take the logarithm of each side. So in this case, for example, 5 to the x equals 62. Well, 62 cannot be written as 5 to a power. 5 squared is 25. 5 cubed is 125. 62 is not a power of 5, obviously. So we need another way to solve. So this is what we do. When I have a variable in the exponent and I need to get it out, I take the logarithm of both sides. Now, it doesn't have to be the common logarithm, but that's the easiest one to use because your scientific calculators let you calculate it really easily. So these are log base 10, even though the 10 is not written. So when I take the logarithm of both sides, remember that when I do that, based on the properties in section 5, my exponent becomes a coefficient. So that frees the x from the exponent of 5. Now I have x times the log of 5 is equal to the log of 62. And then I just divide both sides by the logarithm of 5. Remember that this 5 and this 62 are inside their logarithms. The logarithm of 5 is a whole thing. It's one number. You can't split it up. And then we'll use a calculator to find what that is equal to. So using that same strategy, I would like you guys to try this one. All right, your answer here should be C, 2.5789. Again, be careful with your rounding. And here's what your process should look like. Again, taking the common logarithm of both sides. It does not have to be the common logarithm, but it's probably the easiest one to do for right now. Use properties to bring the exponent down in front as a coefficient, and then divide to get your value of x. All right, so we can do a similar thing with exponential inequalities. We can solve those using logarithms. Again, notice here my base is 3 and here my base is 2. I cannot rewrite 3 as 2 to the power or 2 as 3 to the power, at least not exactly, right? Not precisely. And so we're going to use the same technique that we just did to take the logarithm of both sides so that our exponents will move down in front and become coefficients. So there's our original inequality, and here they're showing you that they take the logarithm. Here they're doing the common logarithm of both sides. So remember, there's a 10 here, even though we don't write it. And then they're going to bring the exponents out in front to be coefficients. Notice the parentheses they put here around the 5x minus 3, because that whole thing has to be multiplied by the log of 2. So I'm actually going to have to take the logarithm of 2 because the logarithm of 2 is just a number, like any number, and I'm going to have to distribute it to 5x minus 3, which is what they're showing you here. 5x times log of 2 and 3 times the logarithm of 2. Now notice what they're doing here. This is all one term, 5x times the logarithm of 2, so they're going to subtract that from both sides. So here I have 7x times the logarithm of 3 minus 5x times the logarithm of 2 equal to negative 3 log of 2. Why are they doing that? Because I need my x's on the same side. Why? Because notice here this is 7 times x times the logarithm of 3, 5 times x times the logarithm of 2. I'm going to factor out my x, and that leaves me with 7 log of 3 minus 5 log of 2 inside. Now this is x times this entire thing. So I'm going to divide both sides by that big long expression that we have. I'll show you what it looks like here. So I'm dividing by 7 logarithm of 3 minus 5 logarithm of 2. I don't know why my pen is erasing itself. And I'm going to do that on the other side as well. So it would look like this. So this side looks really messy, but we're going to use a calculator to evaluate it. So it looks like this. Then we're going to use a calculator to find log of 2, log of 3, and log of 2. Fill those in. And then we'll use a calculator again to simplify. Be careful if you do this all in one step in the calculator. Make sure you use enough parentheses. Make sure you remember you're dividing this numerator by this entire thing. So you have to put parentheses at the end and the beginning of this when you're putting it in the calculator, or else break it up into more steps. All right, so if we wanted to check a point, we could check something that is greater than negative 0.4922. Here they're showing you 0 because that's an easy one to check. And it does work out to be true. 3 to the 0, which is 1, is greater than 2 to the negative 3, which is 1/8. All right, now there's one for you guys to try. In this case, you should have gotten D. Here's what your work could have looked like. There's actually another way you probably could have done it. But take the logarithm of both sides, then bring those exponents down as coefficients. Notice I didn't do that on this side. Why? Because remember, this is log base 10, right, of 10 to the something. So just like I showed you in an earlier slide, if I have log base 10 of 10 to the something, those kind of cancel out. It means 10 to what power gives me this? Well, x minus 2. So I'm just left with the power on that side. If you brought the x minus 2 in front and distributed the log of 10, it should have worked out as the same answer. So then here I subtract x from both sides. To get the x's on the same side, I factor out the x, so I'm left with 3 log of 5 minus 1. And then I divide both sides by this whole thing, 3 log of 5 minus 1, and then you would need to use a calculator to simplify this, and you would get x is less than negative 1.8233. All right, last but not least in this section, very quickly, we have something called the change of base formula. Again, if you have a TI Inspire or a graphing calculator that does algebra like that, the change of base formula, you don't need it as much because your calculator can do this by itself, but I will expect you to know it and be able to show the work for it for the test and quiz. So if I have log base a of some number n, let's say this is not a common logarithm, it's not one I can put in the calculator. I'm allowed to rewrite this as log of another base of n, so the big number here is the one that goes in the numerator, over the logarithm of the base a. Why is that useful? Because then I can take any logarithm, so here logarithm base 3, if you have a regular scientific calculator, you can't do this in the calculator, but I can use the change of base formula, and I can choose to use log base 10. So I can say, well, this has to be equal to log base 10 of 11, right? Or what we would write as log of 11 over the logarithm of 3. And I can choose to use base 10, and now I can use a regular scientific calculator to evaluate that logarithm. So let's look at this. It says express log base 5 of 140 in terms of common logarithms. When they say that, they usually want you to rewrite using the change of base formula. So that might be something you want to make a note of to yourself. And then we're going to round it. So I rewrite, so I take the logarithm of this number here, 140. Notice we're choosing log base 10. And then I take the logarithm of the base, log base 10 of 5. And then I use a calculator to simplify that. And so I want you guys to try this last one. The answer here